The next topic of study is equation of continuity. After the detailed description of the mathematical operators, gradient, divergence, curl, and the idea of fields, scalar field and magnetic field, vector field, then operation of these gradient, divergence and curl operator on the scalar field function and vector field function, their physical interpretation, their mathematical formulation, and the importance application of these. Then after we have seen that how to convert integral equation into the differential form using the Gauss divergence theorem and Stokes theorem. Now the next topic is the equation of continuity, which states that the total current flowing out of some volume, we have considered a cylinder for that purpose, in which I current is flowing, J is the current density and S is the surface area of this wire. So it states that total current flowing out of some volume, this is our volume, total current flowing out from this must be equal to the rate of decrease of the charge. This current which is flowing out from this volume must be equal to the rate of decrease of the charge within that volume. We know that neither charge being created nor destroyed, so automatically this equation of continuity is defined the charge conservation theorem. So since the current is defined as the rate of flow of the charges and the current through the conducting cylinder is I, capital I, is equal to minus dq upon dt. Because this is a solid cylinder, so there will be volume charge density instead of this q, so we have to use that formula. Instead of q is equal to volume integral rho dV. This is in terms of the volume charge density. This is the rate of the volume charge density of this current. So this is minus d upon dt, volume charge density rho dV. So this is the current inside the basically flowing through the conductor cylinder, this particular cylinder. And now this current I is equal to closed surface integral j dot ds in terms of the S, in terms of the current density. So this j dot ds, this is also current, this is also current, so both the currents should be equal through the conducting cylinder I and this at this particular and in terms of the j. So these two equations should be same. So keeping these two equations same, we are getting this result: closed surface integral j dot ds is equal to minus d upon dt volume integral rho dv. Now what we have to do to simplify it, we have to use Gauss divergence theorem, and as a result this closed surface j dot ds converts into the divergence of j. So the result of the left hand side is equal to the volume integral divergence of j dv. Now we have to put this value here. So the right hand side is minus d upon dt, rho is constant throughout the volume, so d rho upon dt, like this one, minus d rho upon dt dv. Now compare both the side. You can write in this way also: volume integral divergence of j plus minus d upon d rho upon dt into the left hand side becomes positive, so this is del rho upon del t dv is equal to 0. As we have considered earlier that volume of the cylinder could not be 0, so this factor is equal to 0. If this is equal to 0, then divergence of j plus d rho upon dt is equal to 0, and from this one can conclude this: divergence of J is equal to minus d rho upon dt, which automatically prove the first statement. The first statement was the total current, divergence of J indicate to the total current density, the current basically which flowing from the surface, outer surface, is equal to the rate of decrease of the charge density, volume charge density. Why decreasing? Because this negative sign is indicating d rho upon dt is the rate of the charge density, basically that is current. On the other hand, and this negative sign is indicating that when you are taking the divergence of current density, it is basically equal to the negative sign of d rho upon dt, which is the rate of the volume charge density. So our first statement was that the total current flowing out of some volume must be equal to the rate of decrease of the charge within that volume. So it means d rho upon dt indicate that this is the factor by which charge is decreasing into the cylinder. But at this point we had not discussed about the type of the current, what type of the current we are using here. So if we include that idea also into the derivation of continuity into this theorem, is there steady state current, direct current, or alternating current, what type of current basically we are using here. So if we use direct current, that is steady state current, in that case d rho upon dt will be equal to 0. If this is equal to 0, that means divergence of J is equal to 0. If divergence of J is equal to 0, it means we know, we have seen this idea earlier also about the del dot E is equal to 0, that is solenoidal. It means total is equal to 0. It means if divergence, if we are considering here steady state current, that means divergence of J is equal to 0. It means the total current which enters at this particular end will be equal to the amount of the current which are coming from this end. So the total current that will remain same. So this is the basically law of the charge conservation theorem. On the other hand, equation of continuity equation is known as charge conservation theorem also. So after this, now let us check the Ampere's formula. We have seen that divergence of J is equal to 0 for the steady state current. Uniform current, that is direct current, steady state current, d rho upon dt is equal to 0. So uniform flow, the amount of current which enter from one end is equal to the amount of current from the second end. So charge conservation, uniform flow of the current into the conductor in case of d rho, in case of the steady state current. But what about the result when alternating current is flowing? That time d rho upon dt is not equal to 0, but equation, continuity equation, indicate the charge conservation into that also. So now first we have to see the Ampere's law, that B dot dl is equal to mu naught times I. Because earlier we had not discussed about the current, type of the current. This current is direct current, steady state current, or this current is alternating current. So the differential form of this Ampere's law is del dot B is equal to mu naught times J. So if I take the divergence of this equation, del del cross B, del dot del cross B is equal to mu naught is a constant, mu naught is a constant, so del dot J. Right, left hand side, this del dot del cross B is equal to 0, so del dot J, mu naught could not be 0, so it means del dot J is equal to 0. So on the basis of this result, when we take the divergence of the Ampere's law, this was the Ampere's law, and right now we are sure that we are using steady state current and taking the divergence of this equation. So then what we are getting divergence of J is equal to 0, and this result we have seen when through the continuity equation, when charge density is related to the steady state current. So it means this law is valid only for the direct current. So Ampere's law is valid only for the direct current. What about the alternating current? If alternating current is flowing, then that Ampere's law is not valid. So Maxwell basically improved the Ampere's law using the idea of displacement current. So now our next topic will be of the displacement current.